Okay, line J1, learn test 3, three-phase distribution center requirements. First thing that we're going to talk about as far as requirements go is going to be mounting requirements and environmental considerations. Obviously, if we're looking at distribution centers, particularly breakers and fuses, things that can be affected by moisture, humidity, and stuff like that, we're going to want to make sure that these things are going to be placed inside of an area where they're going to be dry, and any place where there's not going to be any sort of dangers inside of there. The CEC actually will give you a bunch of different places that they consider to be undesirable for panel boards. They give you bathrooms, clothes closets, coal bins. Who has one of those anyways? But a bunch of places that are either damp, filled with combustibles, that would be like a coal bin, or going to be really warm. If you stick inside of a clothes closet, you have coats and stuff up against there, you're going to trap a lot of heat in there, you're going to have nuisance tripping, and potential for fires as well, because you cannot just effectively bleed that heat off. The other main one that we have for inside of any place where it is a dwelling unit is going to go and be this one that we see over here, which is going to be this maximum of 1.7 meters to the top of our highest mounted breaker, whether that's going to be our main like this, or whether it's just going to be a branch circuit breaker that we are going to go and have here. Doesn't matter if it's a panel, if it's a load center, as long as it's a breaker handle, it has to be no more than 1.7. This is just a accessibility thing that was put in by code. There's a number of things in code that are placed in there for accessibility for people with disabilities, those that are wheelchair bound or anything like that, that they have trouble reaching them. So we have to keep it low enough that somebody from a seated position should be able to go and reach them. 1.7 meters was defined as being that years ago, and it's just kind of stayed inside of our code since. Other than inside of a dwelling unit, if this was inside of a commercial or industrial application where nobody is living in the building, then you have no restrictions. The only thing that you need to be aware of is just that you need to be having some access to the front of it, right? It has to still be accessible, but you can definitely mount these things higher. The top of your breaker can easily be up there at 6 feet, because that's still going to go and be high enough that most people are going to be able to access it. Splitters are also dealt with as far as mounting requirements go. They have to be mounted at minimum intervals not exceeding 1.5 meters. And this is out of the CEC, and what we're showing over here is a pad-mounted splitter, but it could also be a bus type of splitter. And a bus type of splitter looks very similar, except it's going to go and have long bus bars that are going to be inside of here. I'm just going to draw a couple of these out, like that, etc. That are going to be insulated from the back and that we can make our terminations onto. These long bus bar type of splitters are particularly susceptible to fault currents, where if I would go and have a massive short across, so for whatever reason across either inside of the splitter or across cables that are attached on the outside of the splitter, if they would get shorted together, we would go and deliver a large amount of fault current through them. Splitters are generally used where we've got kind of our larger components inside of the service. As soon as we deliver that fault current through there, a large amount of current is always going to go and results in a large amount of magnetic flux that we're going to go and have. And so our flux is going to go up, and since our magnetic flux goes up, that means that we're going to have massive magnetic strains on both our splitter and on the mounting the wall that's on itself. Because the actual buses, particularly in the bus ones, are usually going to be mounted down in a number of places across the splitter, it's then just up to us to go and make sure that we are mounting the splitter box itself to the wall so that it's not going to be able to torque or twist out. Disconnecting switches that are going to be located by our splitter are all going to be covered by that 14100 rule that we talked about before, where we've got a disconnect switch over here and another one over here. Based upon the ampacity of what we require, we're going to go and have these things either really close in or further out. You're going to get worksheets off of this stuff that you can go and work on dealing with these taps we have inside of these. As far as seismic goes, if you've worked in commercial and industrial, you've probably dealt with seismic restrictions before. If you've only worked residential, you probably haven't dealt with them before. But seismic requirements are not part of the Canadian Electrical Code, but they're out of the BC Building Code. And the BC Building Code is going to go and have a requirement for a seismic, not necessarily for seismic wires and stuff to be run and everything, but every public building does have to go and have a seismic assessment. They're going to take a look, they're going to say, is this building in an area where we should be worried about an earthquake shaking fixtures out of the ceiling? If it is an area that is termed as being dead, the majority of BC doesn't actually need to have seismic. But if it is inside of an area like Richmond or Vancouver Island, that's right along the coast and along our subduction zones here, they will go and require it, and then the engineers are going to go inspect that. And what it needs to be is it just needs to go and prevent components, by and large, from falling more than a foot. They're allowed to go and have a little drop. If you get a T-bar ceiling and something drops out, it's allowed to drop, up to about a foot or swing down about a foot, but that's going to be about it. These are going to be specified by engineers once again, and it's going to be just external mounting that we are going to, or external ties that we're going to put to our devices in case there would be failure of the structure. Clearance requirements are going to be a big thing inside of our electrical working spaces. The CEC gives us the fact that we need to go and have at least 1 meter of clear space in front of any sort of electrical equipment. So in front of this electrical equipment, I need to have at least 1 meter of clear space. It should have secure footing, i.e. it shouldn't be uneven or be on a ladder or anything like that, just be a level, flat area. And in addition to that, if I've got any sort of draw-out type of equipment, so if I've got buckets that I can go and pull out of an MCC like we saw before, or if I've got high-voltage draw-out type of breakers, what I have to do is I have to go and measure that 1 meter as being further. So I need to have 1 meter in front of the maximum that that thing is going to go and draw out to. So in this case, if I can draw that bucket out for a full meter, I'm going to need to have at least 2 meters in front. 1 to take up this space and 1 for my actual working space in front of it. Make sure that you go and keep that working space. It's very common that people like to throw stuff in front of the panel because they don't access the panel that often, and they figure, what's the harm in having a couple of old bikes or stuff like that stored in front of it. The problem is not going to be there 99% of the time, but if somebody gets hung up on a live line and somebody can't access it because they're using it as a storage, well, that's going to be a heck of a lawsuit because the CEC explicitly bans sticking any sort of stuff in front of all of my, my working areas here. We need to go and have access so that somebody can enter and disconnect immediately if there is going to be any sort of fault. Egress is another thing covered inside of the code, and this is going to be escape from any sort of a place where there's going to be an issue or something that you want to go and escape from. The general requirement of the CEC is that any room that has electrical equipment has to go and offer an unobstructed means of egress. In other words, a way to exit without any sort of slowing down. As soon as we go and have equipment that gets to be a large value of either current or voltage, so over top of 1200 amps or over top of 750 volts, so high voltage or high amperage type of equipment, if there's going to be a fault off of either of those things, high voltage or high amperage, it's going to be a significant fault. And it's going to be probably a large enough fault that people want to stay, the heck away from this thing. So what you have to do is you have to build your rooms so that if there is a fault, anybody can leave the room without having to pass in front of that fault. Over here we see that on our unit sub over here, we have the high voltage service entrance, the high voltage transformer, and then the low voltage distribution. If the transformer faults, somebody here can exit that way, somebody here can exit that way. If that is not possible, what you have to do is you have to go and make the room deeper. You have to go and increase this. If this was 1 meter before, you would now need to go all the way up to 1.5 meters, so that if somebody was in here and there was no door there, that they would be able to go close to the wall to get out, so they're not super close to the actual fault itself. As far as the doors are concerned, the doors are allowed to be lockable, but they're only supposed to be lockable from the outside. So you can go and use a key to go and get into the lock on this side, but on this side over here, you should be able to just push to get out of this thing or turn it on. There cannot be a lock on the inside because we don't want people that are trapped inside there to not have the tool to go and open it. And generally speaking as well, we're going to go and have the door push outward, because if the door pulls inward like this, it can actually cut back into some of our designated working space that we would need to have in front of here. Ventilation, anytime that we have got an increase in temperature, there's always a chance that we are going to go and have failure of our electrical equipment. Remember that for every 10 degrees over 30, we're going to go and see approximately a 50-degree less lifespan out of any sort of a wound component. That's going to be transformers or motors, which are both considered to be wound. We want to go and avoid having, short lifespan, so we need to go and ventilate. The CEC also goes and gives us a minimum ventilation requirement. So if I have got an electrical room that has hot equipment inside of it, transformers or motors, I need to go and have ventilation. Code specs 3.5 to 4.3 cubic meters, that's 120 to 150 cubic feet of air per minute. That's going to go cycle through the room so that I am going to go and be able to maintain my airflow inside there. If in doubt, if the electrical room is warm, talk to somebody about the fact that this thing should be cooled down, because it will cause long-term issues, not only failures of the equipment, but also a lot of nuisance issues where breakers are going to go and trip when they're not actually close to where they are. Remember, breakers are a thermomagnetic device, which means that thermo, that's that Latin root over there, means to do with heat. They're going to be sensitive to heat. So if this whole room inside of here gets really nice and warm, we're going to start to have breakers, because they're keyed by heat, that are going to start to trip inside of our service. Lug ratings, 3 ratings that we are going to go and consider for lugs. First one is going to be the wire size range. So it's going to go and tell us that, from this size to this size is going to be an applicable lug that I can go and use, etc. We're also going to need to know if it's rated for copper or for aluminum. Not all lugs can be used with aluminum conductors, so it's going to have a CU/AL on them. And then we need to know what the temperature rating is going to go and be of these as well. If it's a 90-degree rating, it should go and have a 9 inside there. To give you an example, the CU9AL tells you that's copper, 90 degrees, aluminum as well for these. If we don't have anything marked, we're going to have to go into the Canadian Electrical Code. If it is marked, we've always got to go and follow our rule 4006, right? 4006 tells us about maximum ampacities that I'm going to be able to go and have for my pieces of equipment. And let's just take a quick look at that. Let's erase all of this over here, and we will draw over top of it. Yep. Over and over. Okay. If I have got 2 pieces of electrical equipment, draw them out over here and over here. And if I'm going to go and have 2 separate temperature ratings for them. Okay, so this one over here is at 75. This one over here is at 90 degrees that they're both going to be rated. And if I got to go and run a cable that is going to go in between these 2, I'm going to go and have to follow 4006. And 4006 tells us that basically whatever I have, my copper or my conductor size comes out of the lower temperature column. So if I'm going to find my conductor AWG, that has to be off of the low side. And if I'm going to go and find my insulation, insulation has to be off of whatever is going to be the higher side. So this side over here would be my insulation, and I would take my wire ampacity out of the 75-degree column into my table 2 or table 4, depending on copper or aluminum that I'm going to go and have. Conductor ampacities are also going to, one way that we take a look at this. The other way that we could take a look at TTRs is I can go and take a look at my lugs that I'm going to go and have. I just erased a whole pile of it there. That's okay. We'll just grab this one over here. Take the whole thing. I don't know. It's not working right now. Whatever. Try that one more time. Delete and there we go. Okay. The other thing that we can have is we can go and have our lugs. If we don't know what our temperature rating is, but if we know what size our lugs are, we're able to go and make a temperature rating off of that. If the terminals are rated for number 1 or smaller, it's going to be 60 degrees. So 1, anytime that the terminals are smaller or equal to number 1, we're looking at a 60-degree temperature that that piece of equipment would go and have. And anytime that it is going to go and be 1 aught or larger that I'm going to go and have, then it's going to go and be 75 degrees for my temperature. So if these 2 were unrated pieces of equipment, but this one had something that was rated for a number 1, and this one had something that was rated for a 1/0 that I was going to go and have over here. This one would be a 75 degree. This one over here would be a 60 degree. Where it gets a little bit more complicated is when I take a look at my ranging that I'm going to go and have across here. You know, if I'm going to go and have 1/0 through number 14 that I could go and have, this one here might be ranked as 1/0 through number 14. I'm going to go and use the higher temperature one that I'm going to have to pick. I'm going to go pick the higher temperature one for my plastic, and I'm going to pick the lower temperature one, which would be the 60 off of this for my aluminum off of these. Once again, there's going to be examples given inside of your binder for this. Last thing we're going to take a look at, and we have talked about this a number of times, is just torque requirements. Everything has to be done to the torque that is rated by our manufacturer. If it's not done to proper spec torque, it is not a correct rating. Now, I know that most connection to the fields happen kind of by feel. You kind of give it a crank, and then you're like, is it like a 1 grunt or a 2 grunt type of tightness that you're going to go and have off of it? This is the incorrect way to do it because we are going to go and have expansion and contraction as we go and get heating up and loosening of our conductors. Over here, what we see is we've got a cutaway of a 3-pole breaker that is going to be attached into my panel over here. It's a bolt-on panel. I see I've got my A phase, I've got my B phase, and I've got my C phase over here. And I can see that my A part of the breaker passes right through there, connects over to the A, the B connects over there into the center one, and the C phase connects all the way over to here. If, for whatever reason, I have got loose connections, right here we've got on our C phase a loose connection, because I'm dropping some volts that are going to go and be across it. I'm going to go and have volts that are going to be dropped. I'm also going to go and create heat at that point. And as soon as I go and create heat, I am going to go and oftentimes cause more arcing and things like that are going to continue to become a self-feeding type of problem. Any sort of a loose connection right over here and a loose connection over here is going to also result in an imbalance in my values of voltage. What I should have, I see from B to C is 208 volts. I got a 3-phase 122 8-volt type of system. But if I take a look at it, if I'm dropping 10 volts, just leaving this one and then dropping another 10 volts entering into here, that would mean that the phase voltage that would be entering into this line C right over here would have dropped 10 on the way out and dropped another 10 on the way out, which means that I'm down to 100 volts phase over there, which is going to be pitted against this 120 volts phase that I'm going to go and have on my B line and 100 volts over here. Results in an imbalance. I'm going to go and have current imbalances if it's a 3-phase load. I'm also going to go and have voltage imbalances over here. It's going to be a low value of voltage on that bus, and every single component attached to it is going to go and therefore be affected. Once again, there's a set of examples that utilize my D6 and D7 tables. Go through those examples and make sure you're familiarized with those tables.